Okay, so now we're going to take a look at one of the other important characteristics associated with your organic compounds and your hydrocarbons by extension, and that is the ability for them to form what are known as structural isomers. Now, it may seem like a complicated term, but really what a structural isomer is, or what structural isomers are, structural isomers have the same chemical formula but different structures. Right, so in other words, they contain the same components, so they have the same number and types of atoms, but they're connected in different ways, and that results in a different structure, which is going to have different properties associated with it, right? You can think of an analogy to a structural isomer if you're familiar with the Transformers movie or the cartoon, right? So if you think of, whatever your favorite Transformer is, let's say it's, Bumblebee or something, well, each of the Transformers is actually a robot, and then it can transform into the Bumblebee itself, which is the car, right? When it does that transformation, all it does is it moves its components around, right? So the tires move around, the hood moves around, etc., and you end up with a brand new structure, something that looks different than the robot. And similarly, when the cartoons back into the robot, obviously they look very different. So you can think of those two things, the car transforming into the robot, those two things you can think of as structural isomers. The same thing can happen on a molecular scale when we start looking at the connections of atoms in a particular compound. So let's take a look at how that can actually happen. All right, so here we have, this is butane. All right, we know that it's butane because there's 1, 2, 3, 4 carbons in it, and we can draw it with the line angle structure as 1, 2, 3, 4. Now, what we can do to make an isomer of this, and this is what you would probably do with some of your other ones as well, is you can take one of the carbons from the end and stick it in the middle. So now an isomer can be something like this, where we have 1, 2, 3 carbons in a row, and then one sticks out from the middle carbon. Right, so if you look at the chemical formulas for both of these, right, butane we know is C4H10, and if you were to count all the carbons and hydrogens in this, you would see that yes, there's 4 carbons, and then there's also 10 H's. All right, so these two have the same structural formula, the same chemical formula, C4H10, but they have different structures, right? And the way that we can tell that these are different structures is just again by looking at that longest continuous carbon chain. So in butane, we have 1, 2, 3, 4 carbons as the longest chain. In its isomer, its structural isomer down here, we have 1, 2, 3 as the longest continuous chain, right? And then we have this one here, another carbon sticking out from that central carbon. Right, so this would be an example, or these two would be examples of structural isomers. Same chemical formulas, but different structures. So let's take a look at how we can draw some other structural isomers. Let's take a look at pentane, right? And the easiest way to start this off is just to draw the number of carbons that you provided with in a row or in a line. So we have 5 carbons, so 1, 2, 3, 4, 5. That's one possible structure. The other ones that we can come up with, we're just going to take 1 carbon from each end and put it somewhere in the middle. All right, so if I have now 5 carbons to work with, I'm going to draw 4 carbons, 1, 2, 3, 4. I'm going to take the 5th one and I'm going to put it right there. Now if you take a look, right, my longest carbon chain in this structure is 1, 2, 3, 4, right? So these are different structures because they have different longest carbon chains, but there is still isomers because they have the same chemical formula, C5H12. Is there another possible structural isomer of pentane? Well, what if I shorten my carbon chain by 1? So instead of having 4 in a row, maybe I have 3 in a row. So 1, 2, 3. And I can put 1 carbon here on that center carbon, and then maybe another one. Remember, carbon likes to form 4 bonds, right? So now I have 1, 2, 3 carbons in a row, but now I have 2 carbons sticking out from that central carbon atom. So this would also be an isomer of those 2. Right, and you can confirm this by coming up with the chemical formula. You'll see that all 3 of these structures have 5 carbons, and they're going to have 12 H's as well. Right, so structural formulas have the same chemical formula, but different structures. What if I instead, let's say, thought about, well, maybe if I 1, 2, 3, 4, and what if I put the 5th carbon over here? Is that an isomer? Well, not so fast, because this one is actually the same as that first one that we drew, because when you count the total number of carbons that you have in the longest chain, right, you can start from the right side here, 1, 2, 3, 4, right, and you have your carbon coming out from the second one. Well, that's the same thing that we have occurring here. So these 2 structures are the same. And we'll address that here in a little bit when we look at the naming of these different structures. Okay, and then we have our 3 isomers shown here, both in the line angle and then also in the condensed structural formula. All right, so by looking at these isomers, what we've noticed is that we're not always going to see alkanes or even hydrocarbons that are just straight chains. What we're also going to see are branches that are coming off of that chain. And the technical term that we give to branches are substituents. So these are branches, and these can be either atoms other than hydrogen, or groups of atoms that extend from, or that are connected to, the longest carbon chain. And these substituents, or these branches, they can come in a couple different varieties. They can be what are known as alkyl groups, or they can be halo groups. And you can probably kind of think where halo comes from. That's from halogens or halogens. What are alkyl groups? Well, alkyl groups are just groups of carbon atoms that are attached to the carbon chain. And we name these according to a systematic way, the IUPAC system, and they're going to have a YL ending. So for example, a 1 carbon branch is called a meth So one, meth is for one, and now it's going to have that YL ending. So methyl. A 2-carbon branch, the prefix for 2 is eth, would be ethyl. A 3-carbon branch would be propyl, etc. In terms, and we'll take a look at these here in a second. In terms of the halo substituents or the halo branches, so fluorine is called fluorochlorine. Cl attached to something is called chloro. Iodine is called iodo, and bromine is called bromo. Right, so those are how we name those halo branches or those halo substituents when they are attached to a longer carbon chain. All right, so here we have some of the ones that we talked about before, and you'll notice here in the case of methyl, there's our 1-carbon branch. You notice it's not CH4 because CH4 would be methane, right? Instead, this 1-carbon thing is attached to a longer chain, so that means we need to attach it, we need to bond it to something else. We need to take one hydrogen away from it, so we have CH3, and then this line here represents the bond to the longest carbon chain, and that's the case for all of these, right? Where you see that bond that goes to, it looks like it goes to nothing, that just means that that's where it's connected to the longest carbon chain. And these are the most common ones that we'll see. All right, and then for the halo ones, right, same thing applies. There's that bond that's connected to the longest carbon chain. I know this looks a little messy, but I just want to make sure that you know what those lines actually mean, because they can be slightly confusing, especially at the beginning. All right, so when we have these substituent groups, or these branches, we need to incorporate those into the name. All right, so the substituents they need to be incorporated into the name, and they're going to be placed in front of the root name, and the root name, remember, is going to be the longest carbon chain. So how are we going to incorporate those substituents into the name? We have to say where they are attached to the carbon chain, right? And the way that we're going to do that is by numbering the carbon chain to give the lowest number possible for the substituents. Right, so we're going to use that number as sort of a location. Maybe the iodine is on carbon number 1 or carbon number 2. We're going to have to include that 1 or that 2 in the name together with the actual prefixes that we saw in the table off here to the left. All right, so numbering the carbon chain then is going to be extremely important because that's going to drive where those substituents are going to be located. All right, so let's take a look at how we can do this systematically. So first thing we want to do is to identify the longest carbon chain, the longest continuous carbon chain. And looking at this one, we can see there's one, if you start on the left, 1, 2, 3, 4, right? That's one option. Or if you go all the way across, 1, 2, 3, 4, 5. All right, now in a chain, you can number from left to right. You can also number from right to left. So maybe this could be carbon 1, that could be 2, that could be 3, that's 4, and that's 5. All right, and I'm going to color code this so we can do a comparison here. So once we have the longest chain, so either way, left or right, from the left or from the right, 5 is the longest. So we know that this has to be some sort of a pentane. Right, 5 carbons, all single bonds, pent and ane. What we have to do is to try to give the substituent groups the lowest number possible. And a substituent group, if you remember, is anything other than an H that's connected to a carbon. So let's go through. We see there's a chlorine here, right? So chlorine is named as a group. Substituent, that's chloro. And then we also have a CH3, right, as a branch, and that's called methyl. All right, so those are our branches hanging off of the main chain. Now we need to say where those are located. And we're going to choose the option that gives us the lowest numbers possible for those things. So if we go and we use the black numbering system, then we see that the chloro is on position number 2. So the way that we denote that is 2-chloro. And then we also see that the methyl will be on carbon 3, so we'd call that 3-methyl. All right, and that's using the black numbering system going from left to right. If we use the purple numbering system going from right to left, we'll see the methyl is on carbon 3, so it'll be 3-methyl. But now the chloro is going to be on number 4 right here. So that would be 4-chloro, right? So when you number it from left to right or from right to left, we're going to choose a numbering system that gives us the lowest numbers possible in total. So 2 and 3 is 5. 4 plus 3 gives you 7. So that means we're going to eliminate the purple numbering system. We're going to choose the black numbering system. And we're going to place these names of the substituent groups in front of our root name for the compound, the longest chain, which is pentane. All right, so we have pentane as our last name, and then we're going to place these in alphabetically. All right, so C for chloro, M for methyl. C comes before M in the alphabet, so we go 2-chloro. And then whenever you have a number and a letter, you always separate them with a dash. So 2-chloro, and then 3-methyl pentane. And that's your IUPAC or your systematic name for this compound, right? So this, when you name it systematically, it should tell you exactly what is there or what's present in the compound. So this is telling us that we have a 5-carbon chain, we have a chlorine on carbon number 2, and we have a methyl on carbon number 3. And that's exactly what we have. All right, there's our longest carbon chain, 5. We have a chlorine on carbon 2, and we have a methyl on carbon 3 as we go from left to right. So one thing you can run into when it comes to having multiple substituents or branches hanging off of the chain, you can sometimes run into a situation where you have multiple or more than one of the same substituent. All right, so for instance, if you have maybe 2 chlorines present, right, then what we're going to use is we're going to use our prefixes di, tri, and tetra to indicate how many of those substituents we have. And we're still also going to use the numbers to say where those, to say where each is located, right? And you actually specifically have to lay it out explicitly in the name. So for what do I mean by that? Well, let's say that we had a structure that looked like this. Let's say we had 1, 2, 3, 4, and then we had maybe 2 chlorines, like so. All right, so the first step that you want to do is you want to figure out what the longest continuous carbon chain is. And in this case, it's 1, 2, 3, 4 is our longest. And I just like to sometimes draw a line around or a box around the longest chain. That way I can quickly see what branches I have. So 4 carbons in a row, that would be bute. All single bonds, butane. And now in terms of the numbering, I would want to number this from the left side. So I give the chlorines, right? These, now both of them are on carbon 2. So I have 2 chlorines, so that would be dichloro. Both of them are on carbon 2, so you actually have to say 2, 2 dash dichloro, right? So you have 2 chlorines, you have to say where each of them is located by using a number for each of those substituents. Right, so it's not just 2 dichloro, it's 2 dichloro. And we'll stick that in front of the name, so this ends up being 2 dichlorobutane. And if you may think, well, Mr. saying that doesn't make a whole lot of sense, why do we need both 2s instead of just 1? Well, if you had something that looked like this, and you had a chlorine here, and a chlorine on that one, right, if you were to name this according to the rules, again, our longest chain here is 1, 2, 3, 4. This is going to be butane. We have 2 chlorines, right, so that would be a dichloro. And now where are they located? Well, they are on carbons 2 and 3 now. So 2, 3 dichloro versus 2, 2 dichloro. Obviously, when you look at both of these, they have the same chemical formula, but now the atoms are arranged differently, so this would mean that these are isomers of each other. All right, so you want to be careful when it comes to the naming. When you have multiple or more than one of the same substituent, you need to use a number for each of those substituents just to say where they're located. Okay, so that's for structures that involve long chains. What about when we run into structures that have a cycle or a ring in them? Well, when we run into these cycloalkanes, we're going to use the same strategy. We're going to name the cycle or ring as the root name or last name. And then we're going to, just like we did with the chain, we're going to name a number, or number a name, I'm sorry. So number the ring. To give the lowest number possible for any substituent that you have. Right, so let's take a look here at this example down here in the bottom right side. We can also draw this if you take a look, we have 6 carbons in a ring, and then that CH2, CH3, that's a 2 carbon chain, so we can draw it like this, 1, 2. Right, so in this case, you want to recognize that you have that cycle or that ring structure. So that would give us cyclo and 6 carbons, hex, all carbon-carbon single bonds, ane. Right, so ring, 6 carbons, single bonds. And now we have this group here, that substituent, which is a 2 carbon group, that's called ethyl. That's the only substituent that we have. So that's ethyl cyclohexane. And in this case, if you only have one substituent on the ring, okay, this is the only case where you don't need a number, because that will automatically be position 1, right? It can't be anything else, because to number the ring to give the lowest number possible, that is going to be carbon 1. So 4, 5, and 6. Note that this 2 carbon group is not part of the ring. It is a substituent, or it is a group that is hanging off of the ring. All right, if we had maybe a couple things connected to the ring, well, then we can take a closer look at that. So for example, if you had the same ring, cyclohexane, and then we had 2 of these methyl groups attached to it. All right, so this is going to have the same last name. So this is a cyclohexane. That's our ring structure, cyclohexane. And then we have a methyl, and we have another methyl. So that's dimethyl. And now we have to number the chain or the ring to give the lowest number possible to those methyls. So in this case, it doesn't really matter which one you decide is going to be number 1, but one of them has to be number 1. All right, so let's just choose the one here on the bottom. So number 1, and then we want to number the chain to give the lowest number possible. So that means we're going to have to go counterclockwise. This is going to have to be 2, 3, 4, 5, and 6. So our methyls are in carbon 1 and 2. So 1, 2 dimethyl cyclohexane. You wouldn't want to go in the other direction. So in the case of if I were to number it in blue, 1, 2, 3, 4, 5, 6. So 1, 2 dimethyl versus 1, 6 dimethyl. The 1, 2 is always going to win, right? So you get the lowest number possible for the substituents in terms of where they're located on the ring structure. So it's the same idea when it comes to numbering that we saw with the chain. All right, so we've seen how to name our structures. What about if we're given the name and we have to draw them? Right, this actually is a little bit more straightforward than going in the other direction. So if you're provided with the name, all right, all you have to do is to start with the ending. Right, so that ending tells you the root of the longest carbon chain. So heptane means 7 carbons. So 1, 2, 3, 4, 5, 6, 7. Now we have dimethyl. So we have 2 methyl groups, and they are on carbons 1 and 2. So which ones are you going to decide? Where are you going to start numbering your chain from the left side or from the right side? Doesn't really matter. You just choose one direction and stick to it. Okay, so I'm going to start from the left. 1, 2, 3, 4, 5, 6, 7. I have a methyl on carbon 1. I'm actually going to change this name up a little bit because I can see this posing a little problem. I'm going to change this to 2, 3 dimethyl. So 2, 3 dimethyl would mean that I have a methyl on carbons 2 and 3. So carbon 2 has a methyl, carbon 3 has a methyl, and all that is just a straight line. Right, remember there's a carbon at the end of each line. At the end of the line there's a CH3. All right, so we had our heptane, our 7 carbons, we had our 2,3 dimethyl, and now we have a chlorine on carbon 1. So there's my bond to a Cl. All right, so that's my 1 chloro, 2,3 dimethyl heptane. All right, you'll notice here, if you were to leave that chlorine out, what we automatically assume is that there's a carbon right here, right? So if there's anything other than a carbon, you have to explicitly write that in. So that's a chlorine, a Cl. That should be on that position. All right, and that's your structure for that name. Similarly, if we are given this one, so we have 3 bromo, 1 chloro, butane. All right, start with the last name first. So butane means 4 carbons. So 1, 2, 3, 4, and then you can number it in whichever direction you want. So that's 1, 2, 3, and 4. I have a bromo on carbon 3, and then have a chlorine on carbon 1, Cl. And that's it. That's your structure for 3 bromo, 1 chloro, butane. So it's systematic, right? So you can always tell exactly what you have in the compound and where everything is located. All right, let's take a look at one more. We'll do this one down here at the bottom. All right, and we have to name that. All right, so the first thing to do is to get the longest carbon chain. So let's see, if we start here, we get 1, 2, 3, 4, 5. I can start down here, maybe 1, 2, 3, 4, 5. If I start on the right side, this is 1, 2, 3, 4, 5, or if I go to the top here, that's carbon 5. Whichever way you slice it, 5 is the longest, right? So 5 carbons. So that would make it a pent. All single bonds would make it a pentane. All right, so let's just highlight where our longest chain is. We'll do that in red. All right, there's our longest chain. Now we have to decide which direction are we going to number it from. All right, and we want to number it to give the lowest number possible to the substituent groups. Where are the substituent groups? Well, they're just hanging off of that chain, and there they are. So we have 2 of those. All right, these are both methyls. And we have 2 of them, so that's a dimethyl. And as you can see now, if we number from the left side, so 1, 2, 3, 4, 5, those methyls are on carbons 2 and 3. So 2, 3 dimethyl, and that's everything that we have in the structure. So we're going to put those in. So 2, 3, and then dash to separate a letter from a number, dimethyl pentane. And that's it. That's how you are going to name this systematically, right? Either get the longest continuous carbon chain first, or the ring, number the chain or the ring to give the lowest number possible to the substituent groups, and then you name a number where they're located as first names in your compound.